Hello everyone, welcome on our YouTube channel. In this video lecture, we are going to learn some concepts of the science. Physics made easy quota help you to learn more about the science. So we are going to understand about the work that in our daily life we use the word work more frequently. A student sitting on a chair learning his lesson usually say, please don't disturb me, I am doing work. But you will be surprised that in terms of physics the student is not doing any work. So we are going to understand about the chapter work, power and energy in terms of the science. So in this video lecture we are going to learn these topics. Please have a look at these topics. So in this video lecture we are going to learn about the kinetic energy. So what is kinetic energy? This is the energy possessed by a body by virtue of its motion. Kinetic energy of a body can be calculated by amount of work done in stopping the moving body or from the amount of work done in giving the present velocity to the body from the state of rest. If a particle of a mass m is moving with the velocity v, then we have the expression of the kinetic energy, that is a half mv square. Kinetic energy is always positive, and we can say that all moving objects or all moving bodies possess always kinetic energy. Like moving vehicles possess kinetic energy, flowing water possess kinetic energy which is used to run water mill. Kinetic energy relates with linear momentum. As we know the expression of the kinetic energy, just multiply and divide this expression by the mass small m, then we get m square v square, and we know that linear momentum p is equal to mv, so we get the expression p square divided by 2m. So kinetic energy can be written in the terms of the linear momentum, that is kinetic energy is equal to p square divided by 2m. We can also frame the expression of the linear momentum, that is p is equal to under root of 2m multiplied with kinetic energy. Work energy theorem is one of the most important concept that relates the kinetic energy and from its initial state and the final state of the object. So according to the work energy theorem, the work done by a force on a body is equal to the change in kinetic energy of the body. So that work done is equal to change denoted by the delta kinetic energy, and change can also be written as the final kinetic energy minus initial kinetic energy. So final kinetic energy is half mv2 square. v2 is the final velocity minus half mv1 square. v1 is the initial velocity. Now we are going to prove the work energy theorem for a variable force. Let dw is a small amount of work done in displacing the object through the distance ds. So the work done is equal to f vector dot ds vector. If a force and displacement has same direction, they are moving along the same line, then the angle between the force and the displacement is 0. So in the scalar form, dw is equal to f ds cos 0 degree. That is, the answer is f into ds because cos 0 is 1. Then we know about the Newton's second law, f is equal to ma, then dw is equal to ma into ds. We know the formula of the acceleration, dv divided by dt, so just change the formula of the acceleration, then do a rearrangement, that ds over dt, and then we have the expression mv dv because ds over dt is velocity. So if w is a work done in increasing the velocity from the v1, that is the initial velocity, to the v2 final velocity, then we can calculate the total work done by taking the integral. So the expression is w is equal to m v2 square divided by 2 within the limits v1 to v2. So solve the expression by first of all put the value of the upper limit then the lower lower limit and get it multiplied with the mass. Then the expression is mv2 square divided by 2 minus mv1 square divided by 2, which means that work done is equal to final kinetic energy minus initial kinetic energy, that is a change in the kinetic energy. If kinetic energy of a body decreases, then work done is negative, that is the force opposes the motion. And from this expression we also can consider if the kinetic energy increases, it means that work done is positive, final velocity is increases and the force supports the motion. Potential energy, the energy possessed by a body by a virtue of its position and configuration. There are the two types of the potential energy. One is the gravitational potential energy, that is the energy possessed by a body due to its position, that is a height above the surface of the earth, and the elastic potential energy possessed by a body because of its deformed shape, and it is either stretched or compressed. So for the conservative forces, we know that gravitational potential energy is equal to the negative of the work done. So we can express the work done in form of the energy and use the expression minus of f vector dot dr. Then we can calculate the total work done by integral it from the limits u1 to u2 for the energy and the displacement r1 to r2. So whenever possible, we take the reference at a point infinity and assume potential energy to be 0 there. So by putting the r1 as infinity, then u1 is equal to 0 and r2 as r. So we have the expression u is equal to, in terms of infinity, minus integral from infinity to r f vector dot dr vector. We must remember that potential energy can be positive and negative because it depends upon the nature of the field. For attraction it is negative and for repulsion it is positive. Potential energy is a function of the position, it does not depend on the path. So for conservative field is equal to the negative gradient of the potential energy. The delta change can be written as a partial differentiate in terms of the different rectangular component. So we have the expression in terms of the partial differentiation of u, that is potential energy with respect to x, with respect to y, and similarly with respect to z direction. So here the partial differentiation of u with respect to x means we are taking y and z as constant. Similarly, when we deal with the partial differentiation of potential energy with respect to y, then the x and z are taken as constant, and this concept is also applicable when we take the partial differentiation of u with respect to z. Equilibrium means the balance. So when several forces acting on the body simultaneously and the net force is 0 on that body, then the body is said to be in equilibrium. It is only possible when the net force is equal to 0 which is acting on the body. So for equilibrium, it means that a body is in translational equilibrium. It will be either at rest or in a uniform motion. If it is rest, then the equilibrium is static because the object is rest. So now we are going to learn that potential energy in the different conservative fields. So first one is a gravitational field. In a gravitational field there is a gravitational potential energy, and its expression is given by minus of g m1 m2 divided by r. And if a body of a mass m is at a height h relative to the surface of the earth, then the gravitational potential energy is mgh. For large distance, that is up to the infinity, h is taken as 0, so the potential energy is 0. Whereas another case is the electrostatic force field. This is for the 2 point charges separated by a certain distance, suppose that is a small r. So the potential energy is 1 upon 4 pi epsilon naught q1 q2 divided by r square. So we must consider the polarity of the charges when we are going to calculate the potential energy. Also, when a point charge q is in an electric field, then potential energy has the expression QV. A charge can be positive and negative, then hence we have the potential energy can be positive or can be written as negative depending upon the polarity of the charge. Potential energy is taken 0 at infinity. So for the spring force field, here the potential energy is due to the configuration of an object. So let x be the expansion or contraction in the spring, then potential energy is given by the expression half kx square. Here the spring constant F is equal to minus kx, that is directed toward the natural length. You can see from the diagrams, the first condition when the spring is at a rest, then there is no displacement. Then we applied the external force and there is the extension in the length, that is increased in the length. When we release the external force, first of all the object compressed by the distance x which it covered initially, then it to move back with the same distance in the form of the compression. Then after some time the object come back to its original rest position. So now the graph show the variation of the kinetic and the potential energy with the distance from the equilibrium position, that is when x is equal to 0. So you can say that the one form of energy is converting into the another form of energy and the total energy is conserved. Here symbol K denotes the kinetic energy, symbol U denotes the potential energy, and E is the total mechanical energy. It shows that energy can be converted from the one form to another, but it can never be destroyed or never created.